Today we're going to be looking at the disk method, and we're going to compare this with volumes of solids of cross-sections and how they differ and how they're similar. We're going to be revolving around a horizontal line. Anytime it's revolved around a horizontal line, it's going to be with respect to x. For vertical, it'll be with respect to y. We'll talk about that in another example. It says find the volume of the solid generated by revolving. So this is different than cross-sections because they pop out of the graph. We're going to be taking these graphs and rotating them. I'm going to show you what that looks like. So the region is going to be bounded by the curve of x equals the square root of y, the x-axis, and the line x equals 2. I can go ahead and tell you that this curve and this curve are the ones that are going to be we're going to be rotating. The x-axis, of course, is just y equals 0. It's going to be bounded by the line x equals 2, and of course wherever they cross. Again, we're going to visualize in just a second. The region is going to be revolved about the x-axis. So the thing about this is if you're revolving around the x-axis, which is y equals 0, right? Then that means everything needs to be in terms of x. If you're revolving about the y-axis or x equals something, everything needs to be in terms of y. So don't get too confused with that. Basically, if the line you're revolving around is y equals something, in this case y equals 0, everything needs to be in terms of x, so the opposite of the line you're revolving. But again, you know, you can consider the fact that the limits or the region which it's bounded by is going to be, if it's in terms of x, then your equation is going to be in terms of x. Did this one a little bit different. I decided to have a step 0. It doesn't really matter. I just decided to label it that way. So the thing is, you want to get y by itself. You want your equation to be in terms of x. Like I said, and I just did this. You know, I could have easily just wrote y equals x squared, but I want you to see that because you're rotating this about a y equals line, in this case y equals 0, everything needs to be in terms of x. So x, we're going to square both sides and we'll get y equals x squared. Pretty simple, right? All right. Now the other one, you know, the other curve that we have, the x-axis, is already y equals 0. Okay, so there's no y in that equation as far as y equals 0. It's already technically in terms of x. Okay, that's 0x. So that one's good. Now we're going to draw the Cartesian plane for step 1. Step 2 is basically already there. You're going to draw the curve on the plane. So this is just like when we did cross sections. All right. So here's our y equals x squared, or x equals square root of y, same thing. And when we sketch it, we can see that it's bounded on the left at x equals 0, and on the right, x equals 2. So how do you know what to get your equation in terms of? Well, it has to be in terms of x. In this case, here again, here's our other curve. It has to be an x in this case because we're going to start at x equals 0 and go to x equals 2. So everything needs to be in terms of that. Okay? And the bottom curve, by the way, is y equals 0. So everything is in terms of x because it's bounded by 0. Okay, step 3 is to draw the shape of the disk. I'm going to explain why it looks this way. Basically, what we're going to be doing is taking this curve and rotating it about y equals 0, and we will be forming disks as a result. Let's go ahead and take a look at what that's going to look like. All right, we are on GeoGebra, looking at an app created by Tim Brzezinski. And for right now, we just have y equals x squared and y equals 0, and it's going from 0 to 2. So what I want to show you is what happens when we rotate this curve. So when we rotate it about y equals 0, you know, the top of the curve, as you can see, forms the outer shape of the disk. And when we rotate it all the way around, we do indeed get a solid, okay? Sometimes it's harder than other times to visualize this, but this is what it would look like from the side. And as you can see, the cross sections here are actually disks, okay? More or less circles, right? And as we go from 0 to 2, those disks get bigger and bigger, and that's because y equals x squared gets further and further away from what we're rotating about. It's almost like a very large horn or something that gets bigger again as you go from 0 to 2. So it's similar to, cross-sectional volume, except that's why it's called disk method. Each cross-section is guaranteed to be a disk, and you could kind of see what each individual disk would look like just by drawing a line going from your what you're rotating about to your curve. Later we'll look at washer method and see how that differs from disk method. Okay, so those disks are going to look like that, and they will form that three-dimensional shape. Step 4 is to sketch the lines of intersection of the disks and the curves. So basically each of those disks are going to look like this. That's just the radius of the disk. When you rotate it all the way around, of course, you're going to get a diameter. Step 5 is to determine the radius of that disk. So the reason we're doing that is because in order to generate the solid, we basically are just finding a bunch of areas of these disks, just like we did with cross-sectional volume. If the region being rotated is above the axis of rotation, this is very important, by the way, the radius is going to be f of x minus a. And in this case, that is what's happening. A, in this case, is 0. It's what we're rotating about. And we can see that x squared is above that. And so our radius is going to be f of x minus a. However, if the region being rotated is below the axis of rotation a, then it would be a minus f of x. So suppose our curve was below what we're rotating about, y equals 0. Suppose it was negative x squared. Then our radius would be 0 minus negative x squared, which of course would give us positive x squared. So to keep that in mind when determining your radius, this simple formula will tell you whether to do a minus f of x or f of x minus a. In this case, it's f of x minus a, so our radius is going to be x squared. What does that mean? Well, for example, let's just look at the very end here. If we plugged in 2 here, we would get 4, right? And that would give us the radius of our entire disk. Again, if we go back and look, it would be the radius of this biggest disk when we're talking about the total solid. Okay, and of course we plugged in somewhere in between, like 1. The radius of our disk would be 1 squared, which is 1. Diameter, of course, would be 2 if you went all the way around. So just a visual representation. All right. But again, we're going all the way across. We're going all the way from 0 to 4. We're going to find basically integrate all of those areas to get the entire solid. All right. So the limits, we're going to be going from 0 to 2. Those disks will be ranging from 0 to 2. That's all that is right there. Now we're going to set up our integral. Now what is the area of a circle? The area of a circle is pi r squared. So we call it the disk method, but each disk is just a circle because it has a radius going all the way around. The volume form is going to be from A to B, so basically these limits from 0 to 2, in this case, of a bunch of circles, dx. In this case, our radius is x squared, but in general, it's just pi r squared. Now what you normally see is, because pi is a constant, you pull that outside of the integral, and it becomes pi from A to B integral of r squared. Again, if you integrate all of these areas of these circles from A to B, it gives you the volume of this big solid right here, which is exactly what we're doing. So here we're going to go pi times the integral from 0 to 2 of each individual radius. Radius is just being replaced by x squared, since that's what it is for each individual one. We are squaring it because, the area of a circle is pi r squared, and then don't forget your dx. So step 7, again, is just to set up that integral. Step 8, make the integrand easy to integrate. If you square x squared, you get x to the 4th. And now we're ready to go. We can integrate x to the 4th using the reverse power rule. Don't forget your pi out front. Integral of x to the 4th is 1/5 x to the 5th. Carry your pi down. We're going from 0 to 2. Notice the 0 won't matter because when you plug it in, you get 0. All we have to do is plug in 2. So we plug in 2 into this formula, and we get pi times 1/5, 2 to the 5th. 2 to the 5th is 32. Final answer, the volume of this solid is 32 over 5 pi. So the volume of this entire solid is 32 over 5 pi. And that's it. It's very similar to cross-sectional volume in that your cross-sections are just disks. So that's what's called the disk method. You're integrating from 0 to 2 of all of those individual areas of circles to get the total volume of the solid. And again, in this case, it is 32 over 5 pi, which as a decimal is around 20.1 cubic units. If you have any other questions about this example, let me know.